Okay, today we'll look at trigonometric integrals and trigonometric substitutions. So the first part is trigonometric integrals. So aim is to evaluate integrals of the form okay, so there are some interesting cases that we can look at. Sine to the power m of x multiplied with cosine to the n of x dx. And similarly, tangent mx secant nx dx. And we can look at sine mx times cosine nx, or sine mx sine nx, or cosine mx cosine nx. Okay, so all these things dx. Okay, so this part is easy, but so these are the things that we can find an algorithm to evaluate. So we'll concentrate on these. So most of the time when you need something like this, a software will give you the answer immediately. So today we'll find out how do they write that software. Okay, so we start with some examples. So for example, let us look at integral cosine cube of x dx. So we take m equals 0. And here the trick turns out to be that the power is odd. When the power is odd, the general rule is, well, the general trick we apply is you take one of these out. Okay, so you have cosine square x cosine x dx. Then you write this in terms of sine. This is d sine. Okay, so we are done. So we write this as integral 1 minus sine square x cosine x dx. So at this point, put u equals sine x, then du equals cosine x dx. Okay, so the integral becomes 1 minus u square du. So you integrate this, u minus 1 over 3 u cube plus c. And of course, you finally put the substitution back. This is sine x plus minus 1 over 3 sine cube x plus c. Okay. So let's again take another example where one of the powers is odd. So integral, so let me look at the example I have. Sine to the power 5x cosine square x dx. Okay, here we have an odd power here, so we take it out. We have sine to the power 4x cosine square x, and I have sine x dx. Okay, so it turns out that sine x dx is d cosine x, give or take a few signs. So I want to write everything in terms of cosines. Okay, so this thing, remember, is square of sine square. So sine square is 1 minus cosine square x, and I have a square. I have cosine square here, and I have sine x dx. Okay, so again, put u equals cosine x, then du equals minus sine x dx. So this thing becomes minus integral 1 minus u square square u square du. Okay. So this thing becomes minus, so let me just copy it from here now. U squared minus 2u4 plus u6 du. Okay, so I continue to carry this minus here. This is 1 over 3 u cubed minus 2 over 5 u5 plus 1 over 7 u7 plus c. Now put back u equals cosine. Okay, so this becomes minus 1 over 3 cosine cube x minus 2 over 5 cosine to the power 5x plus 1 over 7 cosine to the 7x plus c. Okay, so minus plus. So why did I change this one? And this one becomes minus. Okay, so this is the general idea. Remember, we have a formula for, we have a reduction formula for sine to the power n. Let us look at a similar formula for cosine. For small powers, of course, you don't need a reduction. Okay, so recall that we have a reduction formula integral sine to the power n x dx is equal to, so let me write what this was, minus 1 over n cosine x times sine n minus 1x plus n minus 1 over n integral sine n minus 2x dx. Okay, so repeatedly applying this, we find an antiderivative for the nth power of sine x. Okay, a similar formula. Similarly, look for a reduction for integral cosine nx dx. Okay, so to save some ink, let us recall this integral in. Okay, so this is integral cosine to the power nx dx. Okay, so we check what we did here. Okay, so we try it here. If it works, we are fine. If it doesn't work, then we'll try to find something creative. Here we did integration by parts. So here, try integration by parts. By parts, where I take u equals cosine n minus 1 x and dv, the other one, cosine x dx. Okay, so this is generally what we try to do. Okay, then du is equal to minus from cosine n minus 1 cosine n minus 2 x sine x dx. Okay, and v is sine x. Okay. Now integration by parts says that first we multiply this and this, so we have cosine n minus 1x sine x minus, I have another minus here, so plus n minus 1 integral cosine n minus 2x, and I have sine square x dx. Okay, we write sine square x as 1 minus cosine square x. So this thing becomes cosine n minus 1x sine x plus n minus 1 times. Okay, so this times this is I n minus 2. Okay, because we call this I n. now I'll have n minus 2 here. And I have minus n minus 1 times I n. Okay, so this thing is equal to I n. Okay, so I take it to this side. I have n of these. So I divide everything by n. I have 1 over n cosine n minus 1 x sine x plus n minus 1 over n I n minus 2. Okay, so we have a reduction formula also for cosine. Okay, so you see that we just had a sign change. Okay, so you see the general rule for these things is if one of them is odd, okay, so I'll do that. If one of them is odd, we can explicitly integrate this. Okay, I'll do both of them. So using these two, now we know that how to integrate, well, actually how to find an algorithm when the power of sine and the power of cosine are both even. Okay, so. Okay, so what is this for? Now we look at the case. The power of sine is an even integer, and the power of cosine is another even integer. Okay, so you choose one of them and write it in terms of the other. Okay, so sine square can be written in terms of cosine square and vice versa. So here, let's do it this way. Sine 2mx, and this is cosine square x written to the power n x. Now this is of the form, of course, sine 2mx 1 minus cosine square x 1 minus sine square x. Okay, so the answer will be in terms of integrals of this form, and from there on, we'll rely on an algorithm. Okay, so this is 1 minus sine square x over n dx. Okay. So recall here that we have the binomial theorem, a minus b to the power n is equal to summation k equals from 0 to n minus 1 to the power k, and choose k. I'll use the other way, a n minus k b k. Okay, because since this is symmetric, it doesn't matter which one you start with. Okay, the sign is the power of this must be the same as this one. Okay, so we'll use that. Okay, if we use that, the integral becomes, just for the fun of it, sine 2mx times summation k equals from 0 to n minus 1 k, and choose k. Sine my b is sine square, so sine 2k x dx. Okay, so we take all of this out. Okay, so summation k equals 0 to n minus 1 k, and choose k. Integral sine 2m plus 2kx dx. Okay, so now for this, use reduction formulas. We have those reduction formulas, so if you are writing a program for this, use reduction formulas for these. Okay, so it doesn't, you don't have to do this by hand. The nice thing is that we can now solve it and explicitly without using approximations. Okay, so this is what happens when the powers of them are odd, both even. Let's take one power odd. in that case, we have an exact formula without going to reduction anymore. Here you have to use reduction formulas depending on the power. Okay, so suppose now we have integral sine mx cosine 2n plus 1x dx. Here again we use the idea that works so much, sine mx. This is now cosine square x to the power n, and I have an extra cosine x dx. And I write this, okay, so let me write this. Sine mx, 1 minus sine square x to the power n cosine x dx. Okay, so now we put, okay, so now put u equals sine x, then du equals cosine x dx. So the integral continues to become, okay, so integral u to the power m, 1 minus u square n du. Okay, so again we use the same binomial formula for this. Okay, so it's nice when you can explicitly solve something. Um times summation k equals 0 to n minus 1 k, and choose k u 2k du. Okay, so you see this one suddenly becomes something very easy. K equals 0 to n minus 1 k, and choose k integral u to the power m plus 2k du. Okay, so suddenly we have something trivial to integrate. Okay, so k equals 0 to n minus 1 k, and choose k. We integrate this. This is u to the power m plus 2k plus 1 over m plus 2k plus 1 plus a constant. Okay, now put back here. Put back u equals what was u sine x. Sine x. Okay, so you have an explicit formula, and choose k sine to the power m plus 2k plus 1x divided by m plus 2k plus 1 plus your integration constant. Okay, so this thing is explicitly equal to this. Okay, as an example, with numbers, so that we believe what we are doing. Okay, I looked at this one, sine 4x cosine 7x dx. Okay, so here m is 4. Okay, m is 4, n is 3, right? 2 times 3 is 6 plus 1, 7. So you just put those integers here, and what you get is the following. 1 over 5 sine to the power 5x minus 3 over 7 sine cube x. No, sine, it's increasing. Sine 7x plus 1 over 3 sine 9x minus 1 over 11 sine 11x plus c. Okay, so if you take the derivative of this, and every time you have sine, keep writing it in terms of, every time you have cosine, keep writing in terms of sine, simplify, and eventually you'll have this. Okay, so let's do exactly the same thing, but this time the odd power is here. Okay. Okay, so this is now integral sine 2n plus 1. Okay, I put n here so that the formulas will look similar. The places of m and n will not shift. It will look more beautiful. Okay, sine x cosine m x dx. Okay, so again, this will be 1 minus cosine square x. So this is sine square, and I have sine to the power 2n. I have cosine mx, and I have the extra sine x dx here. Okay. So as we did before, we put u equals cosine x, then du equals minus sine x dx. Okay. So the integral becomes minus, so this minus comes here. Integral, this thing is 1 minus u squared to the power n times u to the power m du. Okay, so we again do the same thing here. Okay, let's write this. So this is, now I'll take this minus into the expression here. Okay, so here I have minus 1 to the power k, and in this example I have a minus here, so I'll make it k plus 1. Okay, so this is integral u to the power m summation k equals from 0 to n minus 1 to the power k, the normal formula. The minus there will change the sign and choose k u to the power 2k du. Okay, so this, so again, I'm integrating u to the power m plus 2k. Okay, so when you integrate this, this is k from 0 to n minus 1 to the power k plus 1, and choose k. And you have u m plus 2k plus 1 divided by the power plus a constant. Okay, now put back, so put this thing back. You have summation k equals 0 to n minus 1 k plus 1, and choose k cosine m plus 2k plus 1 over m plus 2k plus 1 plus a constant. So this one can again be, so you see the formulas are almost the same, except you change the sign, and of course you change sine to cosine. So again, let's write a similar expression, changing these numbers. So example, we have integral sine 7x cosine 4x dx. Okay, so again, m is equal to 4, n equals to 3 in this example. So you have the same coefficients, but the sign changes, okay, because the formulas are symmetric, except that one of them is minus 1 times the other, and signs are changed into cosines. So minus 1 over 5 cosine 5x plus 3 over 7 cosine 7x minus 1 over 3 cosine 9x plus 1 over 11 cosine 11x plus c. Okay, so we covered all cases. When both powers of sine and cosine are even, you choose one of them and write it in terms of the other, and then you use a reduction formula. When the power of one of them is odd, you take one factor out and write everything in terms of the other. when both powers are odd, okay, it doesn't matter. You can choose any of them and use one of those two things. So this covers the integration of sine times cosine. Of course, these algorithms you program when the powers are large. If the powers are small, you can do it by hand in a few steps. You don't need to. It takes less time to do it by hand than typing it on the screen. Okay, now let's go to tangent and secant. Remember that we again have an identity between tangent and secants. 7. Now for tangents and secants. Okay. So here we have 1 plus tangent square x is equal to secant square x. Okay, we are going to use that. In the previous one, sum of the squares was 1. Here, the difference of the squares is 1. So we'll use this. Okay, so let us look at the case when when one of them is even. In this case, that will be easier. And of course, here we have also tangent x derivative is secant square x, and derivative of secant x is secant x tangent x. Okay, so this tells us that we have to use a different algorithm. In the previous case, derivative of one was the other. Okay, so plus or minus. So we used a different technique there. Here, we will keep these in mind. So one case is when the power of secant is even. So tangent x to the power, okay, let me put the power here. Tangent m x secant square, secant 2n x dx. Okay, so here n is greater than or equal to 1. So here we notice this one. Okay, secant square, one of these squares is going to be derivative of the other, and the other squares can be written in terms of tangent. Okay, so that's what we will exploit. So this is going to be tangent mx secant 2n minus 2x secant square x dx. So we will write this thing in terms of tangent. Okay, so integral tangent mx secant square is 1 plus tangent square x. So this gives me secant square. I have the power n minus 1. And I have here secant square x dx. Okay, so now I can put u equals tangent x, and everything will work. Okay, so here put u equals tangent x, then du is what we have there, secant square x dx. So the integral becomes u to the power m, and 1 plus u squared to the power n minus 1 du. Okay, so I'll stop this here because we know what to do after this. You'll use binomial formula to write this as a polynomial, and then multiply by u and integrate. So, okay, so I'll say easy. Okay. So suppose now the power of this is even. No, the one. Well, here when we don't cover all the cases. Okay, so it's not as straightforward as the case of sine cosine. So the next case is again n greater than or equal to 1, and we have tangent 2n plus 1 x, okay, m, and secant nx dx. Okay. So in this case, we take 1 here, we take 1 from here, and we have tangent square x to the power m. Okay, and I have secant n. I'll take one of them out. So what did I take out? I took 1 secant out, and I took 1 tangent out. Okay. So tangent square I can write as secant square minus 1. So this becomes integral secant square minus 1 to the power m. I have secant square secant n minus 1 x, and I have secant x tangent x dx. Okay, now I can do substitution. Okay, so now put u equals secant x, then du is secant x tangent x dx, and I have all of these there. So the integral becomes u square minus 1, u square minus 1 to the power m. So this was m. Okay, and I have u to the power n minus 1 du. Okay, so again, you use binomial formula. The rest is straightforward. Okay, once you reduce it to a polynomial form, so the rest is easy. Okay, the other cases we don't know. The other cases, okay, we don't have a straight way. The other cases you have to use integration by parts to break it, because when you use integration by parts, you change the power of one of them. Okay, so for the other cases, use integration by parts, and keep your fingers crossed. Okay. So we don't have command on everything. Okay, so we have this. Okay, so let us look at another case. So what do we do when we have integral sine mx cosine nx dx? Okay, so we have formulas for products of these things. Okay. So maybe it's time you wake up. Here, use the identity sine mx cosine nx equals 1 over 2 sine n minus mx, or rather the other way around, sine m minus nx plus sine m plus nx. Okay? So you see, once you write it, then you don't get anything exciting. Okay? Then this becomes, you write this here, you get 1 over 2 integral sine m minus nx dx plus 1 over 2 integral sine m plus n x dx. Okay? We all know how to integrate sine. So this gives the answer. Okay, so similarly you use the others. Okay, so do you remember the formula for? So here we use, so for these cases we need the trigonometric identities sine ax times sine bx is equal to And then sine AX cosine BX is equal to, and what else? Cosine AX cosine BX. If I remember correctly, we had formulas for these things. How do you find formulas for these things? Okay, one way is to look it up at Wikipedia. What's the other method? Yeah, we try addition formulas and we try. So what are the addition formulas? Okay, so we can use addition formulas. So let's see, we have two addition formulas. Sine A plus B is sine A cosine B plus sine B cosine A. Okay. And if we put a minus sign here, we have another formula. And then we have cosine A plus B. Let me put minus here. And this is cosine A cosine B. Then the sign is reversed here. Minus plus sine A sine B. Okay, so now you try to be creative and obtain these formulas from here. Okay, anybody will try to, who wants to try the first one? Okay, so while you are thinking there, maybe I ask you another question. If you solve this problem, then we'll take an early break. So let me find a nice formula. Okay, let's do this, this one. So integral from 0 to pi over 2. Integral from 0 to pi over 2. And cosine 5t. Well, you have to use this line. Cosine 5t sine something. Cosine 5t cosine 10t. Okay. Let's solve this, and then we'll take a break. There must be a formula in the book. Okay, you can look it up. Come on, let's solve this and let's go to Mozart before every other class so that we can pick whatever we want without standing in the queue. The formula in the book for cosine is, so we use cosine A cosine B equals, let's see what the book says, 1 over 2 cosine A minus B. Or is the minus first? Yes, A minus. With cosines, it's always the wrong order, plus cosine A plus B. Okay, so to develop these formulas, you write all of these four things. Okay, so you write all of these four equations, and then we want a product of cosines. Okay, cosine A, cosine B will appear at two places. Okay, so you solve it, you add them, because cosine A, cosine B will appear here, and it will also appear when you have minus here. But then the sign of this will change. So when you add them, these parts will cancel, and you'll have a formula for cosine A, cosine B. If you want a formula for sine A, sine B, then instead of adding them, you subtract one from the other, then cosines cancel. You have a formula for sines. Okay, so this is how you play with these formulas. So when you do that, you get this. Okay. So what do we have? We have 1 over 2 integral from 0 to pi over 2. Okay, cosine a minus b in this case is 5, right? Cosine 5b, cosine 5t dt plus 1 over 2 integral from 0 to pi over 2. Cosine ab is 15 in this case, cosine 15t dt. Okay, so what is the first one? Antiderivative is plus or minus sine times some constant. What is the antiderivative of cosine 5t? Sine 5t, and then you do this. Okay, let's try if this works. We have 1 over 2. Then the antiderivative of this must be sine 5t. But if you take the derivative of this, you get 5 extra. So I don't have 5 there. So I do this, and 5 is here, right? And I evaluate this from 0 to pi over 2. Okay, so that is it. Plus 1 over 2. Now I'll do the same thing. This is sine 10t divided by 10. Okay, so I check. If I take the derivative of this, I'll get cosine. No, this is 15, right? So this is 15. I'll get an extra 15, and then I have to get rid of this. 0 to pi over 2. Okay, so what are the values now? Cosine. Okay, so let's continue. Now, when I put t equals 0, I will get 0. Okay, so I'll take those out. So the first one is 1 over 10 sine 5 pi over 2 plus 1 over 30 sine 15 pi over 2. Okay, so what are those numbers? Well, you get powers of pi over 2. Okay, so you have to count here. Okay, so 1, 2, 3, 4, 5. Okay, so this is 1, right? Okay, so 1 over 10. What is the other one? Huh? Minus 1. Okay, so minus 1 over 30. Okay, so I take no responsibility for this. You said 130. Okay, so what is the difference? 1 over 15. Okay, so it works. Okay, so let's take an early break. Okay, so next hour we'll do some substitution, and then we'll have a quiz.